Hi, so we're back and we'll be talking about still describing motion with graphs, but our graph now is velocity versus time graph or a VT graph. And in a VT graph, our x-axis is still time, but our y-axis is now velocities. Now, using velocity time graphs, we can actually benefit from velocity time graphs in two ways. One, the area under the graph gives us the displacement of the object, while the slope gives us the acceleration. So remember that the slope in VT time graphs give us acceleration. For PT graphs or position versus time graph, the slope tells us about the velocity. For this one, in VT graphs, the slope tells us about the acceleration. Let's take a look at this one. We have an object that is moving with a constant velocity. And when we say constant velocity, then therefore, the velocity does not change throughout the observation period. So we have here our values. We have at 0 second, the velocity is 10 meters per second. After 1 second, it's still 10 meters per second. After another second, it's still 10 meters per second. And it's still 10 meters per second all throughout the observation period. If you graph these values in a velocity time graph, so of course, these are positive velocities. So you plot them in the positive side of the y-axis. And of course, taking into account the second as the x-axis. So these are our points for this motion. And then you just connect all these points, and then you have there your graph. Now again, any graphs that are horizontal will give us a slope of 0. Since the slope is 0, and as we mentioned earlier, that the slope of the graph in a velocity time graph will give us an information about the acceleration. Now, if we solve for it, we have the slope is equal to y2 minus y1 over y2, y1, and x2 minus x1, which is, if we take these 2 points, so let's say this is 0.1 and this is 0.2, we have 5 or 10 meters, you have 10 meters per second minus still 10 meters per second. As you can see here, there, it's 10 meters at 0.1 and 10 meters per second at 0.2. Over 5 seconds minus 0 seconds. And that will give us 0 meters per second over 5 seconds. Which will give you, will give you 0 meters per second squared as the slope. And slope of the graph in a VT time graph is your acceleration. Therefore, if the slope is 0, acceleration is also 0. Which makes sense because constant objects with constant velocity has no change in velocity. Therefore, the rate of change is 0, since acceleration is the measure of the rate of change in velocity. Now, if we have a changing velocity or an object that is moving with changing velocity, so we have here an example. At 0 second, the velocity of the object is 0 meters per second. And then after 1 second, it's sped up and it's now 10 meters per second. And then after another second, it's sped up. It's now moving at 20 meters per second. And then now at 30 after another second, and then 40, and then 50 meters per second. So if you see, in every time interval, the velocity of the object changes. And as you can see here in the diagram, in each time interval, the change in position now varies. There's no constant change. Or, there's no regular interval when it comes to the position of your moving object. So here, we have these values, and if you plot that in the velocity time graph, you have 0 seconds at 0 meters per second, and then the second one, then If you connect all of these points, so you have graphed these values here, all these values, then you will get a graph that looks like this one. In a velocity time graph, the slope tells us about the acceleration. So if we solve for the slope, and as you can see, the graph has a straight line, or the slope is a straight line, which tells us that the slope is constant. And if the slope is constant, then acceleration is constant as well. So if we solve for the slope, which is your acceleration, then which is y2 minus y1 over x2 minus x1. And remember, in a velocity time graph, your y2 and y1 are actually your velocities, and your x is actually your time. So if we take 2 points again in the graph, let's take this one's as 0.1 and this is 0.2. Your velocity 2 is 50 meters per second over, or minus 0 meters per second, all over the time is 5 seconds minus 0 seconds. And that will give us 50 meters per second over 5 seconds, which is 10 meters per second squared. So this is the slope, but also it's the acceleration of the object. So as you can see here, acceleration is equal to 10 meters per second squared, which is also the slope. Therefore, the rate of change in the velocity here, this 10 meters per second squared, also means 10 meters per second per second. So that means in every second, there will be a change of 10 meters per second in the velocity. So as you can see here, after 1 second, there's a change of 10. After another second, there has been a change of 10 meters per. So that's how you interpret acceleration. Now, analyzing two-stage motion. When you say two-stage motion, we have here a change in the motion of the object. So as you can see here, the graph, you have two parts, the one that is horizontal and the one that moves upward to the right. So of course, you have two different values for your acceleration. Since the slope has changed, then acceleration will also change. And if you look at our table of values at 0 seconds, or at 0 second until 4 seconds with an S, the velocity is the same at 2 meters per second. Then after the 4th second, so you can see here, it started changing. The velocities are now increasing. So how do we solve for the acceleration here? Of course, you just need to solve for the slope. And looking at your slope from 0 second to 4 seconds, you can actually immediately conclude that the acceleration is 0 meters per second squared. Why? Excuse me. Why? Because you have there the graph, which is a horizontal line. And a graph that is horizontal means that the slope is 0. But if we still solve for it, you have acceleration, which is equal to the slope at this graph. Then, of course, y2 minus y1 over x2 minus x1. Let's take these points here as our points to be considered in this equation, or in the solution. So the y2, or the velocity, is 2 meters per second, minus, still it's 2 meters per second. It did not change. Over 4 seconds minus 0 seconds. 0 second, which will give you 0 meters per second over 4 seconds. And that is 0 meters per second squared. So just actually by looking at the graph, you can immediately conclude that it's 0 meters per second because it's horizontal. Then for acceleration, between 4 seconds to 8 seconds, then that is in question. We can solve for it again using the slope. So the slope is equal to y2 minus y1 over x2 minus x1. Now if we take these points at 4 and 8 seconds, your y2 or your final point will be 10 meters per second minus the velocity at 4 seconds is 2 meters per second over you have 8 seconds minus 4 because we are only measuring between these time intervals. And that will give you 10 meters per second minus 2 meters per second. That's 8 meters per second over 4 seconds, which will give you an acceleration value of 2 meters per second squared. All of them are positive. So what does this 2 meters per second mean? That in every second, there's a change in velocity at 2 meters per second. So as you can see here, it's actually correct because the difference here is 2 meters per second. The difference here is 2 meters per second. And the difference here is 2 meters per second as well. Let's move on. Now, again, the importance of the slope. The slope in a velocity time graph reveals information about the acceleration. If the acceleration is 0, then the slope will be 0 or a horizontal line. If the acceleration is positive, then the slope will be positive. If the acceleration is negative, then the slope is negative or a downward sloping line. To visualize that, let's have uh, the graph of a positive velocity and a negative velocity, or an object moving with a positive velocity and negative velocity. Remember that our x here is the velocity, or our y-axis is the velocity, and all velocity values above your time axis or x-axis is positive. Therefore, if the graph is in this area here, the velocity will be positive. Even if it's a positive slope or it has a negative slope, if it's in the positive area of the velocity, which is above the time axis, then the velocity is positive. On the other hand, as you can see here, the graphs are below the time axis or the x-axis, which means that our y values, which are velocities, are negative. Therefore, the velocities are negative as well. We're just looking into where the graphs are. So by looking into where the graphs are, you can conclude either if the velocity is positive or the velocity is negative. Now, speeding up versus slowing down. This graph here, from positive 3 meters per second, or the object is now moving at 9 meters per second. It moves away from 0 meters per second. So you can tell that the object is speeding up if it moves away from 0 meters per second. Here, from positive 3 meters per second, it's now positive 9. Your velocity increased. This one, you have negative 3 meters per second, and then it's now negative 9 meters per second. It's still increased. But you will ask, isn't negative 3 greater than negative 9 in the number line? Yes, that's correct. But remember that in physics, especially when dealing with vector quantities, the negative sign indicates direction, which means that the velocity is still increasing, but it's moving towards the negative direction. The magnitude is still getting bigger, but the direction is opposite. Since it's negative, it has the negative sign. Again, positives and negatives indicate direction. Now, this is slowing down, as you can see here, from positive 9 meters per second to positive 3 meters per second, since it moves towards the value of 0 in our velocity. Of course, when you move towards the 0, then the value is decreasing. As well as this one, negative 9 meters per second, it's now negative 3 meters per second. So it's slower now compared to the first values. So speeding up, moving away from your positive x or your x-axis, slowing down if it moves towards the x-axis. Next, so relating the graph to the motion for VT graphs. This graph here represents a constant rightward velocity. Why rightward? Again, you can identify the direction of the velocity of an object in a velocity time graph by looking at where the graph is placed. So since the graph is here at the positive side of the y-axis, then it has a rightward velocity or a positive velocity. It's constant. The velocity is constant because your line is, or your graph is horizontal. This one, you have a leftward velocity because it's placed here in the negative side of our values for velocity. And the motion is also constant because you have a horizontal line. If you remember, in PT graphs or in position time graphs, a horizontal line will mean the object is not moving. But for VT graphs, the objects can still be moving, but the motion or the velocity remains the same all throughout the observation period. Next, we have this one. We have rightward velocity with a rightward acceleration. So how did we arrive at that conclusion? You can identify again the direction of the velocity according to where it's placed. So since it's placed in the positive side of our velocity values or above the x-axis, so you will have positive velocity. Now, how do you identify the direction of the acceleration? Again, the slope in a VT graph tells us about the acceleration. The slope here is positive. Therefore, the acceleration is positive. On the other hand, this one, it's still in the positive side or above the x-axis. Therefore, velocity is positive. But the slope is negative. Therefore, the acceleration is negative as well. As you can see here in the diagram of a moving car, for this one, we have a rightward velocity, which has a rightward acceleration. This one, rightward velocity, but with a leftward acceleration, which means it slows down. This one speeds up. The first one, it speeds up, and then the second one slows down. Now, this one, you have your graphs which are placed below your x-axis. Therefore, your velocities are negative, or they are directed towards the negative direction. Now, how about the acceleration? Just look into the slope of the graph. Since this one, the slope is negative, so we can tell that the velocity is negative since it's below the x-axis, and acceleration is negative because the slope is negative. On the other one, you have a positive slope, therefore the acceleration is positive, and it's placed below the x-axis, therefore the velocity is negative. The velocity is negative. So as you can see here, the velocity is moving towards the negative direction, and it's speeding up because the acceleration is in the same direction as your velocity. For this one, you have a leftward velocity. Oops, let me redo that. Your acceleration is, or your velocity is leftward, but your acceleration is rightward. Therefore, it slows down. So as you can see from a bigger value for velocity, it's now slower. So that's how we can interpret the acceleration and velocities of object in VT graphs by just looking into where the lines are and the slope of the line. Now let's interpret the motion, or let's describe the motion of these objects using these graphs. So in interval A, how can we describe the motion of the object? So in interval A, you have a positive velocity, which is constant. Why constant? You have a horizontal line in interval A. So that's constant. Positive velocity since it's in the positive side. How about the acceleration? So acceleration will be zero acceleration. Acceleration. There. Now, for interval B, what happens? For interval B, your velocity is still positive because it's still above the x-axis. How about your acceleration? Is acceleration 0 or not? So since there's a slope, the slope is not 0, then there's acceleration. But is acceleration positive or negative? So how will we identify that? Again, we look into the slope. The slope is negative because it's moving downward. Therefore, you have a negative acceleration. Okay? Now for C, interval C, you have here another horizontal line, which will tell you that your acceleration is 0. Your acceleration, and you have still a positive velocity. But the velocity at interval C is slower than the speed or the velocity in A, because as you can see here, it has a greater value for velocity compared to C. Now, how about the other one? Let me divide it. Okay. This one, interval A. How do we describe the motion of the object? So in interval A, since you have a negative slope, then you have a negative acceleration. Is the velocity positive or negative? The velocity is positive. Why? Because it's in the positive side. Now for interval B, you can see here in interval B, it's horizontal line, meaning the velocity is constant. But the velocity is 0 meters per second. Why? It's in the x-axis already. It's 0, which means that object is at, oops, let me place a space there. Object is at rest. Why? The velocity is 0 meters per second. And if the velocity is 0 meters per second, therefore there's no change in position. So in interval B, our object is at rest. So know the difference. If the horizontal line is not or just above or below your x-axis, then the object is still moving, but with a constant velocity. However, if the horizontal line falls in the x-axis, which your value for y is 0, then your object will be at rest. For interval C, how will you describe the motion of the object? The graph is now below the x-axis, therefore your velocity is negative velocity. Now, how about the acceleration? Is it positive or negative? Again, you look into the slope. The slope here is negative because it goes down. Therefore, your acceleration is also negative. So that's how we interpret these lines in a velocity time graph. So that's for the first benefit of velocity time graph, which is being able to describe the acceleration of the graph. Now, let's look into determining the area on a VT graph, which tells us about the displacement of the object. So let's take a look first of definition of displacement. Displacement can be calculated using the formula velocity times time, since you remember velocity is equal to the change in displacement over time. So displacement, if we transpose this one there, we have displacement is equal to velocity times time. Okay? Since velocity times time gives us displacement, the area under velocity versus time graph also gives us the displacement of the object. So let's take a look at this example. We have here the graph. So this is our graph, the line. And we can actually form a rectangle out of it. As mentioned, we can solve for the displacement Diba? Displacement is equal to velocity times time. We can solve for the displacement if we solve for the area of the graph. So using the given graph, calculate the displacement of the object for intervals 0 second to 4 seconds. Now, this is a rectangle, and how do you solve for the area of a rectangle? The area of a rectangle is actually just base times height, correct? If this is our base is time, and our height is velocity. So velocity times time, which is the same as this one. So therefore, displacement is equal to area of the rectangle. Solving for it, so you have the area of the rectangle, which is base times height. Our base is 4 seconds times our height is 20 meters per second. Cancel seconds. You will get 80 meters. Therefore, the displacement of the object that is being described here is 80 meters. Positive, since it's positive. Another one. Calculate the displacement of the car from the given graph. Now, as you can see here, you have a two-stage motion again. You have different slopes, or the slope has changed, especially in this part. So what you can do actually is just to divide the shape, or divide the graph and form different shapes. So you have here one rectangle and one triangle. You just need to solve for this area and this area. Oops. The area of a rectangle and the area of a triangle, and then just add them. So area of triangle plus area of rectangle, which will give you the total displacement. Because again, the total area in the graph tells us about the displacement. So first, we solve for the area of the triangle, and we know that the area of the triangle is 1/2 base times height. So 1/2, our base here is just, of course, since we took the shape from 0 to 2 seconds only. So you have 2 seconds times the height is, you have here the height, 20 meters per second. Cancel the seconds as a unit. So you have 1/2 40 meters. And you'll get 20 meters. So that's for the area of a triangle. This is 20 meters. Plus, we need to solve for the area of rectangle. Rectangle is equal to base times height. And the base here in our rectangle, in the rectangle, which is from 2 seconds to 6 seconds, and that is 4 seconds. Have here 4 units. And then the height is still 20 meters per second. And that will give you 80 meters. So plus 80 meters, which will give you 100 meters as the total displacement. Therefore, the object here, or specifically the car, has a displacement of 100 meters, taking into account the entire area of